Okay, so welcome back to the calls, and today we have another interesting topic that is called as evolutionary robotics. So we'll be combining the two things that we learned so far. The first one is evolution. Things evolve. They take in interesting shapes. They take in interesting patterns. They take in values such that your solution is optimal along with time. And swarm robotics, where we saw a lot of small miniature agents being able to display interesting pattern, whether aggregation, collective movement, dispersion, chaining, whatever we displayed and we program for that app. So today we combine the power of both these interesting topics into a topic called as the evolutionary robotics. Now you would wonder that what we did is with Swarm Robotics was interesting. They did produce interesting simulations for the ones who've done the lab exercises very religiously, and you could see excellent animations around. But then there's a problem. So, from the class assignments to the lab tests, I changed the question a little bit, and you have to do a lot of programming. So you have to think that, okay, now this is the question. So this has to be my rule base. This is how the rule should move. This is how the forces should be modeled. And then once you simulate it up, you're like, oh God, what is this happening? Okay, maybe these two need to communicate and send some information on a channel, and I need to account for that. There was so much of a programming to be done. And with that also, you sometimes get the results and sometimes you do not get the results. If you get the results, you get a clap. Of course, you get good marks. If you don't get the results, then I'm a generous person. I still give you marks. So, wouldn't it be wonderful now that we are talking about machine learning? Nobody should write down the rule based system, the logic based system. The machine should learn on the data on its own. Wouldn't it be wonderful if we apply the same kind of primitives for swarm robotics? So we say, why should a human make a rule base for a swarm of robots or for a single robot? Why can't the robot learn on its own? So we take birth in this beautiful world, we learn how to walk, we learn how to talk, we learn how to do things many times on our own. So wouldn't it be wonderful if the robots just take birth? Yes, somebody assembles the robot and you put it in this beautiful world, you put it in the lab, you put it in your office, you put it at your home, and you just power it on. The robot learns everything on its own. It learns all the interesting behaviors on its own. It's acting in the world and it's doing everything up. Now we've used this motivation into something called as reinforcement learning already. Not in this course, but in a course called as artificial intelligence. We looked into reinforcement learning, where we said exactly the same thing, that you've got a robotic agent. The robotic agent acts in the world. It keeps on doing interesting things. And everything that it does, it gets in some kind of a reward function. It gets some kind of a reward, and the agent tries to maximize its own reward and reduce its own punishment. So, are the two domains exactly the same? And the answer is to a very large extent yes. So we'll be making in a new kind of a reinforcement learning system, not the kind of systems that we looked into the course on artificial intelligence. And this new kind of system, all that it'll do is that a robot or a team of robots will display some skills, display some things, we'll adjudge it, we'll say it's good or it's bad, and using that, what it'll do is it'll try to program itself up. It'll try to write down its own programs. It'll try to make its own models. It'll try to act autonomously without requiring you to write down or to program a robot ever in the future. So let's look at it. So I said that I'll have something called as the robot. So it should take in some input and it should take in some output. And of course, we know that for any system AI based, the sensors are the inputs and the actuator is the output. So in Swarm Robotics, what kind of sensor did we have? We took a sonar ring so that the robot can know the distance from the obstacles around. So the sonar beam goes, it comes back, only using which it knows what is the distance around. Sometimes we took in sensors like a bump sensor, we took in a sensor like a microphone. So using a microphone, the robot knew the proximity to the other robots, or sometimes an array of these sensors. We use some light sensors to detect LED lights. So whatever you have it, just give it to the robot. Just give it to the robot. And what type of actuators did we have? We basically had a left wheel and a right wheel, or we had a robot which can be controlled by a linear speed and by an angular speed. And again, that's exactly the same as reinforcement learning again. The sensors were the inputs, the actuators were the output. So now what's this robot? It needs to be something which is programmable. It needs to be something which is a program. So a program will take the from the eyes and convert it to the muscles or the hands. So that's going to be a computer program. And of course, what I will do is I will make an artificial neural network that takes all the decisions. So machine learning, artificial neural network. So let this machine, let this robot train itself. That's my long-term aim. Let this robot train itself. Now, in this particular situation, I don't have for any given sensor like this what will be the actual actuator reading. So I cannot use a supervised kind of a training. I cannot use supervised learning. There's no data set. And therefore, obviously, I'll go in for the reinforcement learning where the robot will see, look at the world, what it needs to do using all these sensors. The sensor readings will be given to an artificial neural network as an input, and the neural network equations, whatever we've seen, will calculate what is good output and supply to the output layer neurons. And here is where I collect it up. And what does the robot do? Once I get this actuators, then I take this actuator values and I apply it physically on the robot, and that is what in AI we call as the environment. And that moves the robot. So again, the sensors are invoked, and of course that's the, you call it as a sense, plan, act cycle, or you call it as a control loop of the AI based agent. This is what keeps on happening. Now the problem is that I've said that it's an artificial neural network and it needs to be learned in a reinforcement learning framework. Why not supervised? I don't have a data set. The robot will have to itself act, find out whether it did something good or bad, and decide on its own. The interesting thing over here is again that I did not write down a deep learning. I wrote in an artificial neural network. If the same thing would have been a more sophisticated robot with lots of sensors, HD LiDAR, HD cameras, and all those high data rate sensors, I would have said too much of data. So I need a deep learning neural network for that. Here we are talking about just 5-10 sonars. Just two, three microphones, one bump sensor. So the sensing is as low as possible, and a traditional neural network, we hope, will be able to do that, will be able to learn in such a framework. So now that's not the class on reinforcement learning, so I'll not tell you why am I not using the actor critic method, the deep Q networks, the Q networks, and so on and so forth. I'll go with whatever we have learned just before it, which is to use neuroevolution as a means to train it. So it's trained using the primitives of neuroevolution. Still, you want to know what's the difference between neuroevolution and reinforcement learning. So let's talk about, in a supervised sense, what's the difference between a backpropagation algorithm with mini batches, incremental learning, and a neuroevolution. So one of them uses just one agent, and that tries to keep going down, 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 down. In neuroevolution, you've got the entire population pool, and they try to convert. So backpropagation algorithm, incremental learning, mini batches is single agent, and neuroevolution is multi-agent search in the weight space. So similarly with deep Q learning, they're all single agent, and that agent tries to go down, down, down in the weight space. We're using neuroevolution, so it's a multi-agent search, or we'll be using many individuals. So now it really turns out that I don't need to do anything, and the picture is up and the picture is ready, and we can just apply a normal neuroevolution over it to get this trained network. And once I have this trained network, I'll just plug it into the software of the robot and it'll work perfectly. Now there's a little bit of a problem with these sensors, and let us take an example. So I've got my robot which is around over here, so that's maybe a sonar sensor, and let's say it's traveling around over here, and there is another rival robot which is over here that is coming over here, let's say with a simple similar program, or this one is a human. Now how do I really avoid this robot? Do I avoid it like this, but then that assumes this one is static? By the time I come here, this would come here, so I should avoid it like this. But maybe this is traveling at a too high speed, and if it's traveling with a too high speed, I might even go back a little bit to avoid a collision, and that's how I do it. However, instead, if this one was traveling in this direction with a large speed, I would have just gone in around over here. So obviously, a navigation function is a function of the distance to obstacle as well as the relative speed with the obstacle. That's why we used methods like the velocity obstacle method that accounted for the speed of the obstacles relative to the robot in order to calculate a feasible and a good speed, in order to calculate a feasible and a good velocity. However, here, if I use this neural network, it is getting the sonar sensors as an input. It's not getting the speed as an input. So how do I do that? How do I do that? Now, in this example, if the robot just travels straight for a second or so, then speed is nothing but difference of the current sonar reading minus the difference of the previous sonar reading divided by the time interval between the two readings. So that's a relative speed of this with respect to this, and that's a good enough information. Now, it's easy to say that, okay, it depends upon the speed, but why not it also depends upon the acceleration? Maybe it depends upon the acceleration as well, and therefore I should need to measure the relative acceleration as well. Now, luckily, we don't need to worry about all this because we've got a model very well studied in machine learning approaches called as the recurrent neural network. And unlike a traditional neural network, the only thing that it has that it has cycles. So that's my input layer neurons. That's the hidden layer neurons. And this is the output layer neurons. This is a normal backpropagation. This is a normal feed-forward neural network. If it's recurrent, it can have lateral connections like this, making in cycles. So the output of this neuron is the current input, and the previous output of this neuron. So what I really need to do in order to compute speed, this is the input of the sonar sensor readings. This neuron adds one delay. Let's say this just adds one delay. So what I do is I take the current reading, I take the one delay reading, I take in the difference using weights +1 -1, and that's how it goes around over here. So a recurrent neural network can obviously calculate the first derivatives with enough neurons. It can calculate the second derivatives, third derivatives, fourth derivatives, whatever derivatives you want. It can calculate infinite derivatives subjected to model complexity, and therefore the decision in a recurrent neural network is not only based on your current input, it is in fact also based upon the input to all the past inputs and their interdependencies. Like for us, the difference of the sonar reading was important to calculate the relative speed. Sometimes the triple derivative may be important to calculate the first derivative speed, second derivative acceleration, third derivative jerk. If it's not needed, the system will not find out those features. That's like the feature engineering done by the neural networks themselves. If something is important, those features will be found out. If something is not important, those features will absolutely not be found out. And therefore, let us obviously change this model from an artificial neural network without any change into a recurrent neural network. And it really turns out nothing changes in neuroevolution, be it a artificial neural network, acyclic, or be it a recurrent neural network with cycles. The primitives of neuroevolution will remain exactly the same. They will be absolutely unaffected. So the stage is set, and what we really need to do is probably to show you one iteration of the neuroevolution using these recurrent neural network as an example. So let's get started. So what happens in neuroevolution? The first step is generation of initial population, and the initial population, of course, are random recurrent neural network, and I know how to have them as phenotype, as a library implementation, as a Python implementation, as a MATLAB implementation, or as a genotype where I note down the weights and the biases and the architecture separately. And I note down the weights, biases, and architecture separately and make a phenotype for that. So generation of random neural network is absolutely simple. And then what do? Is I calculate the fitness of each one of them. I rank them up so that I can do calculation of expectation value. Expectation value is proportional to rank. Rank 1, highest expectation value. And I do a selection, I do crossover, I do mutation, I do architectural mutation, I do generation of the new population pool. Now, let's really think about, because I've got this bigger picture, that the recurrent neural network is actually a physical robot with step changes in neuroevolution, so that we only talk about those steps. We don't keep upon talking all the other steps that would be irrelevant. So Does crossover change? No, the crossover remains exactly the same kind of crossover that we saw in neuroevolution. Does mutation change, either parametric or architectural, either changing the weights and the biases values or adding new neurons or changing, deleting neurons or adding connection or deleting connections? No, it does not change. Uh, Neuroevolution mutation operators will not change for this application. So in fact, the neuroevolution that I discussed was pretty much generic. I have an application of neuroevolution. Why should it change any step? So selection remains the same, crossover remains the same, mutation remains the same, generation of a new population pool remains the same. The only thing that changes is the next step, which is fitness evaluation. So previously all my examples were of fitness evaluation supervised in nature, and they were supervised in nature, so I had my fitness value of an individual X was given by the submission over some training data, my phenotype. So that's X. So let's say input number I given the weights and biases in X minus the target. Regularization parameter. So now I cannot use this one because there's no such training data. Now I don't have a training data. I cannot use this one. So there is no training data. So I'll change this obviously into a reinforcement learning framework. So now we'll see that how to calculate the fitness function value in a reinforcement learning framework, or in other cases, or saying out in some other words. Now my problem is that I'm dealing with a recurrent neural network, and because I'm dealing out with a recurrent neural network, the way that I calculate the fitness function value is bound to change, and that's the only new thing that will come in this entire picture, the way that you calculate the fitness function value. So let us do that. So now let's say that I have an individual X whose fitness function is to be calculated. Why I know, because where does neuroevolution use fitness evaluation? So what I'll do is, first of course I'll convert genotype X, or that's what I do in every neuroevolution. So that's not just because I changed supervised to reinforcement. That happens every time. So I convert a genotype into phenotype. So convert X from genotype to phenotype, or I just had a linear array of weights and biases, and I convert it into an actual MATLAB ANN object that can be used. Now what do I do is I load X phenotype as a controller on the physical robot. Okay, so I load X, which is a phenotype. It's a recurrent neural network as a Python library, as a controller on the physical robot. And we've used this terminology multiple times. So we said the BFSM, it effectively changes the controller of the robot. You have the first behavior, and then you say that, okay, let's go on to the second behavior because of a change of state. So you change the controller of the robot, and exactly the same thing is happening, that you say that the physical robot and its all embedded system, Raspberry Pi Arduino, instead of having the first whatever controller was loaded, will now have this neural network as the controller. You can also do it at the electronics level. So I load in this new thing as a controller on the physical robot. And then what do I do is, now I've got a robot which is ready. The robot is already physically at some place. Wherever you opened it up, it's there at that lab. And now it has a controller. It's already powered on. And therefore what you can do now is that now you can simulate. Oops, it's a real robot. And I say run the robot with this controller for t seconds. So I just run the robot for t seconds. Now that I run the robot for t seconds, one thing that I know of is that now, because the robot has executed, it has run for t seconds, I assess how good did the robot perform. And I say fitness is equal to my assessed score. And that's all. So it's something that's pretty simple. It's something that is pretty obvious. So all that I do is that I had a physical robot. I just got it from the market. I gave birth to the robot. So it's there at my physical lab. And all that I do is that I had random individuals. I had random recurrent neural networks. So I need to calculate fitness of all of them. So I say that, okay, let's start over with the first neural network. I load it on top of the robot. The individuals that I have, maybe as a genotype, I convert it to a phenotype, which is a standard ANN model. I load it onto the robot, and once I load it onto the robot, I let the robot run. And then I just look at the robot and I give it marks that you get 5 on 10, you get -6 out of 10, you get 8 on 10, you get 9.9 on 10. So you're really doing good based on how good the robot has done. So that's why it's reinforcement learning. So I don't have any data. All that I had was I let the robot do whatever, and I provided a score to the robot. And once I provide score to the robot, I've got the fitness function value of one individual in the population pool. I can do it for all of them. I can sort them by get the ranks. Once I get the ranks, I can do expectation value calculations. I can do selection. Once I do the selection, I'll pair and do crossover. I'll do mutation, structural mutation, parametric mutation. Once I do the mutation, I will take the old and the new population pool and decide how do I make the new population pool, and this thing will go on and on and on and on and on. So that's what I really go upon doing.